For section 10.1, it's titled Using Properties of Tangents, but this is also our first section in the chapter on circles. So we're going to have to first go through a few terms we're going to use throughout the chapter. First off, a circle is a set of all points in a plane equidistant from a given point. So we should be familiar with what a circle is, but it's not a polygon, something we talked about last chapter. It is literally a set of points all equidistant from one point, which we'll think of as in the middle. So all these points going around come together to give us a circle. It does not have sides. It's not a polygon. Again, they're a set of points. Now if I identified that circle with a A at the center, I'd call it circle A. And we're going to identify them by the center. Now, a radius is a segment whose endpoints are the center and a point on the circle. So I can draw a segment here, call it AB, that starts at the center, ends on the circle. It's a segment, and it'll be our radius AB. A chord is going to be a segment whose endpoints are on the circle. Now, where a radius has an endpoint at the center, the chord is going to have its endpoints on the circle. So I could call that chord CD. Next, we have a diameter, and a diameter is a special type of chord. This would be a chord that contains the center. So if I moved down this chord so that it lined up, so that it went through the center, let's call this one EF, that would be our diameter. Now, since we have that diameter, we also may remember that a diameter is twice the radius. It's really two radiuses put together. I have the radius here and a radius here. So let's add our other names for the radius. AE and AF are also a radius. Next, we look at more shapes that are going to be outside the circle. These first three, radius, chord, diameter, are going to be within the circle. They'll have either an endpoint on the circle, or in the case of a radius, an endpoint in the circle. When I go to a secant, that's going to be a line that intersects the circle at 2 points. A secant is going to have some portion of it outside the circle. What portion, we're not sure. We just know that it has some part of it outside the circle. Now, maybe it's just a segment that ends on the outside, maybe it's a ray that keeps going, or maybe it's just a line that goes on infinitely. Either case, it's going to have something outside the circle. So it's a line that intersects the circle at 2 points. A tangent is going to be a line that intersects the circle at 1 point. Now, if we tried to draw a line that would intersect the circle at 1 point, there's a few ways we could try, but we'd eventually be something that's going to go through and make it a secant, unless it comes in and hits that 1 point on the circle. So that's going to be our tangent. We'll give it 2 points here, I, J. And then we have a point of tangency to go with it. And that'll be point I, and that's just a point on the circle where the tangent hits it. Okay, so if we look at applying these now, we have an example. So we have to determine whether a line, ray, or segment is a radius, chord, diameter, secant, or tangent. If I look at AC, AC is a segment. It's going to be a segment that starts at A, ends at C. It ends on the center of the circle, so that's going to make it a radius. Segment AB starts on the circle, ends on the circle, so that's a diameter. We have to be careful not to call that a chord, even though it technically is a type of chord. The fact it goes to the center, it is a diameter. We have DE, that starts at D, goes through E, but it hits the circle at point B. That makes it a tangent. Now also realize we could have also called it DE like this, or even as a segment, and the fact that it comes in and hits the circle at 1 point, it would still be a tangent. And last we have AE, starts or hits A, hits E, keeps going beyond there, but it hits the circle at points A and G. That would make it a secant. Okay, now let's look a little bit more at tangents. We have something we call common tangents. Now this could be a line, ray, and segment again, and that's tangent to two coplanar circles. So this line hits both circles at 1 point. If it does that, we're going to call it a common tangent. It's a tangent to that circle, it's a tangent to that circle, it's it's a tangent to both circles, meaning it's common tangents. We have a few different ways we could look at common tangents. When I have two circles that don't have any points in common, I actually have 4 different common tangents. And these all go in and they hit each circle at one point. There's 4 of them. When I have circles that share 2 points, I'm going to have 2 common tangents, a top and a bottom. When I have 2 circles that share 1 point, I'm going to have a top, a bottom. Oops, let's try it that way. And I'm also going to have one that's at that point they have in common. So that one has 3. And when I have one circle inside another, I actually have no common tangents, because if I think of the tangent...
All students who are not participating in an extracurricular activity at this time, please report to the front of the school to wait for your ride.
If I think of the tangent that's on the outside of this circle, it's never going to quite get inside to be a tangent to the other circle, so that one has none. So 4, 2, 3, none. Okay, now let's look a little bit more at tangents, because that's really what this section is focused on. Our first theorem says, in a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. So what that is looking at is it's saying this line M here is going to be tangent to the circle if and only if it's perpendicular to QP. QP we can also think of as the radius. So I can make this right angle here, or even go further and think maybe a right triangle there. Now, why we would bring up a right triangle is we can use right triangles, or we can use Pythagorean theorem to get to right triangles. So a way we're going to see is to actually use Pythagorean theorem to show that it is perpendicular and it gives us a tangent. So we'll really see 2 types of problems. So in this first one, let's say we're given these values and we have to show that it would be a tangent. Maybe that's how the question is posed. So we would do 37 squared equals 12 squared plus 35 squared, because if this turns out to be true, that would tell us this would be the hypotenuse, we'd have a right angle here, and we would have a tangent. So 37 squared is 1,369. 12 squared is 144, and 35 squared is 1,225. I combine those and I get that they are equal. So the fact they're equal means I have a right triangle, and this would be a tangent. Now, another way you may see it is when they have our radius as our unknown, as our variable r. In this case, I'm going to call my longest side here r plus 5, because it's the distance from here to the edge is r, the radius, and then 5 more. So r plus 5 squared equals r squared plus 8 squared. Now, if I simplify the right side first, I get r squared plus 64. But we have to be careful with that r plus 5 squared. It is not r squared plus 25. We can't just distribute an exponent like that. We have to go back to our algebra days, and this is just squaring a binomial, or maybe multiplying 2 binomials. You can use the FOIL method, maybe you've used the box method. We can do the box method real fast. This is where I write r plus 5 and r plus 5. I just multiply the rows times the columns. I get r squared, 5r, 5r, and 25. I then combine like terms. I get r squared plus 10r plus 25. And if you use FOIL, that would also work too. Okay, so from here now I can simplify. But I have an r squared on both sides, so I can subtract it from both sides. I have 10r plus 25 equals 64. That becomes 10r equals 39. Is that 39? Let's double check. Yeah, 39. I divide, I get 39 over 10, or 3.9. So our radius here would be 3.9 units. The key thing you're going to see there is where you have to square that r plus 5. Got to be careful with that one. Okay, moving on, our next theorem of tangents says that tangent segments from a common external point are congruent. So, if SR and ST are tangents, they hit the circle at one point, and we can even go further to say that they're perpendicular to a radius we can draw, then we know they're the same. So, it can look as simple as one of these. I could say 28 equals 3x plus 4. Common tangents are going to be the same. So, 24 equals 3x, and x would equal 8. Now, the reason we get to this, that these common tangents are the same, is actually because we can make two right triangles. We have a reflexive line from S to P. We have radiuses that are the same, and we have a side, side, and an angle, but since it's a right angle, it's by hypotenuse leg. So really, we've snuck in right triangles again to actually show up here to help us find that. But when we have tangents that go to the same point, they're going to be congruent, so we can set them equal to solve. So we're going to finish up with a couple examples. So we're kind of integrating each one we've done. So the first one, determine whether we have a tangent to our circle. Here I'm going to test, and I want this to be by Pythagorean theorem, that 18 squared equals 9 squared plus 15 squared, because if that's true, that makes this the hypotenuse, which means this is a right angle, which means AB is a tangent. For 18 squared, we get 324, and that's equal to 81 plus 225. 81 plus 225 gives me 306, which is not equal, so we're going to say not a tangent. Next one, we're going to have our r again, so we're going to say our hypotenuse that we want is r plus 16 squared equals r squared plus 24 squared. I get r squared plus 576 on the right side. When I square r plus 16, it is not r squared plus 16 squared. We're actually going to use the box method, and when you do that, you get r squared plus 32r plus 256. I can now subtract the r squareds from both sides. I get 32r plus 256 equals 576. We then get 32r equals 320, and r is 10. So if they ask for our radius, it would be 10 in this case. Last one we have, here we have common tangents. So we're going to say that x squared equals 9. If I take the square root of both sides, I have x equals the square root of 9. We've got to be careful here, because by taking the square root of 9, we actually get that it's plus or minus 3. Because it's not asking us for the value, plus or minus 3 do work here. Because we could put in a positive or a negative 3, square that quantity, and it could come out to be 9. Now, be careful in the future here, because if it was just an x by itself, I wouldn't pick negative 3. It couldn't be an option because we couldn't have a negative length. But by the context of this problem, it would be plus or minus 3.